Okay, chapter 4 of S2, sampling theory. I think I'm rolling chapter 4 and 5 sort of in together, really. We need to have some notation and really have a good understanding of some words, first of all. Say that I wanted to work out the average height of year 13 students. And as part of this process, I took a sample of year 13s. And my sample was made up of Josh and Sam Newton. Okay, so I have a sample there. And from that sample, I could work out X bar, where X bar is the sample mean. Yeah, okay, it's a sample mean. Okay, now we need, rather than just saying mean, this is where we need to be careful about adding the word sample mean. But then I could think, well, I'm going to do another sample, okay? Maybe that wasn't the best idea. Maybe I'll do a bigger sample. Maybe I will sample and I will measure Chloe's height and Tom and Ed's height. Okay? And then what will happen? I will get another sample mean. Will it be identical to the first sample mean? Not necessarily. Okay? So what I'm going to say is that's x1 bar, that's x2 bar. I have a first sample mean and I have a second sample mean. Now, I think I completely ignored Ben. So I could have another sample.
Just 10.
Of just Ben. Okay? I could average Ben and I would get, a third sample mean, x bar, x3 bar. They are all sample means. Okay. Now, what am I actually trying to find out? I said I want to find the average height of year 13. What am I actually after? I want two words. One of them is going to be that one. The first word will not be that one. I know what you mean, but it's not the word total that we use. So we're beginning with P. Population mean, yeah. So what I'm really after here is the population mean. And what notation am I going to use for the population mean? Nice try, but no. Think about what we have done in chapter 2, maybe. The mean of the population. Mu, yeah, okay. So the population mean will be mu. That's what I'm really after. What would I have to do to find mu? To find mu, the population mean, so in brackets, what would I need to do? There's only one answer for this, and it's an unpleasant answer in some ways. Yeah, I would have to measure every single member of year 13. So I would need to measure every member of the population, which is sometimes impractical. Here, I could, in theory, measure, if I change my population, the average height of year 13 students who are present today, in theory, I could go around and measure everybody's height. If I wanted to do, for a bigger population, it's just impractical, and to be honest, I wouldn't even do that. You would do a sample, okay? So, we don't know mu, so what that leads us into is we need to estimate mu. We're going to estimate the population mean. And the estimator we will use, so we will use X bar as an estimator, or as an estimate, yeah, as an estimator. Now, I've got three different X bars up here. Which one might be the one closest, do you reckon, to mu? The middle one. Why is the middle one?
Because you've got the largest sample size.
And here, yeah, okay. So we can say that as n increases, where n is the sample size, I think we can sort of generally say that we would expect x bar to get closer to mu. So, I'm just going to make some numbers up now. Let us say we had 3 different x bars. Okay. Josh and Sam, what do you think your mean height was? I need a number from you within 2 seconds. 182. Okay, we'll talk this in centimetres. Thank you. Chloe, Tom and Ed, what do you think your mean height was? I need an answer from you in 2 seconds flat. 176, good, okay. And Ben, what do you think yours was? 180. 180. Okay. So what we've got here, if I just do a little graphy thing and label this x bar, I've got 176, got a value there, I've got a value of 180, and I've got another value of 182. Now, if I put up the side my frequency of getting those, well, I'm just going to get a bar chart looking like that. Okay, but x bar here, it's possible for x bar to take different values. Now, you guys all gave me integer answers. Why was that? Answer, because you were lazy and you weren't really thinking it through, and I asked you to do it really quickly. Okay, but it's very unlikely. Well, okay, with 3 people it could have been that, but these numbers here could be, well, they're continuous, aren't they? They're averaging continuous measurements, so they themselves could be, or will be, continuous. So actually, x bar itself is a continuous random variable. So x bar itself is a random variable. It can take different values. Now, if I did this on a much bigger scale, and I was doing this for the height of year 13, and I took a much larger sample size, I would probably get something looking like this, and this is just a rough sort of drawing. Okay? I would probably get samples, some small samples, some big some samples where the value of the mean was small, some samples where the value of the mean was big, but more samples where the value of the mean was in the middle of the range. What is that suggesting? Okay, so yeah, that is basically a normal distribution thing. You would expect if you took lots of samples here, if each vertical line wasn't one sample, it may be that's like 1 sample, 2 samples, 3 samples, 4 samples, 5 samples, 6 samples. There may be 30 samples represented on there. But generally, you get more sample means in the middle than you do at the edge. So here, if this red curve was a normal curve, like a normal bell curve, then bang in the middle here by symmetry would be your mu. And what we actually get is, because x bar is a random variable, it will have an expected value. So I probably ought to be using a capital X there because it's a random variable. And the expected value of x bar, in other words, what you expect the average x bar to be in the long run, is unsurprisingly equal to mu. Yeah, okay. So, important things we've got from here. X bar itself is a continuous random variable, and the expectation of x bar is mu. Now, before we go any further, we were here measuring the heights of year 13. Have we made any assumption about those heights, so the original data set? That it is accurate, okay. Did we make any assumption that the data we were measuring itself was normally distributed? Did we say that? Actually, it doesn't matter. When you are dealing with sample means, whatever distribution the original data came from, the sample means will follow the normal distribution, regardless of what the original one was. Because it's like you're taking means, and they're like in the middle and just collecting them all, you still get this shape. Okay? So, if we can write down whatever distribution x follows, x bar will always be normally distributed. Now for a normal distribution we put the mean in here. The mean is the same as the expectation. We have already said today the expectation of x bar is mu. If we are doing a normal distribution, what goes after the mu? Sigma squared. But sigma squared measures the spread, how spread out, how wide the curve is. What do you think we could do to narrow the curve? The area would still be the same, the height would go up. But to narrow the curve, to get better estimates, what do you think we could do?
Larger sample size?
Yes. So if I divide there, basically as the sample size gets bigger, the variance here will get smaller. Okay? And that sigma squared there, just make it that sigma squared is equal to the population variance. Population variance. Okay? And that mu is equal to the population mean. And n was the sample size.
So you would always have a constant sample size as opposed to some with 3 and some with 2?
Well, not necessarily, but you'll see that as we come through. No, we won't. Okay, and you'll see that as we go through. But this here, well, including that bit there, I suppose, that is called the central limit theorem. Okay? And just as a normal distribution was pretty much fundamental to everything we did or do afterwards, that central limit theorem is going to be fundamental to everything we are going to do from here on in this unit.